Hello everybody, and welcome to exercise 1 on page 146. And this is going to be our first example of using the divergence theorem that we just derived to calculate a flux integral. Okay, so let's read this problem together. They're giving us a vector field, yi plus 3x plus zk, and they'd like us to find the flow of that vector field through the cube that we're seeing over here to the right. So the outside surface of the cube, we're trying to measure the flow of this vector field through that. Okay, so in mathematical terminology, what we are trying to find is the flux integral, f dot dA. Okay, and using the divergence theorem, we're going to take that integral and replace it with a triple integral. Okay, and in that triple integral, there are going to be some pieces involved. So anytime you use the divergence theorem, there is a surface, which in our case is the outside surface of the cube. One important property that that surface has is that it's totally enclosed. Okay, in other words, that cube totally encloses a solid three-dimensional region in space. To use the divergence theorem, your surface has to have that property. Okay, in other words, there's a region inside of it that we could call W that's solid. So we'll call that the solid inside of the cube. Okay, and what the divergence theorem says then, let's write it down, remind ourselves here. This flux integral that we're looking at is actually equal to the triple integral over the inside of the cube of the divergence of our vector field dv. Okay, so to do this problem, we need to calculate this triple integral. To get started, we need the divergence of our vector field. That's a calculation that we have to do. So let's remind ourselves what our formula for the vector field is. It's here. Okay, and so if we just go over here to the right and do that calculation, the divergence is about taking partial derivatives and adding them together. There's no I component, so we just need to take the derivative with respect to y of the j component plus the derivative with respect to z of the k component. And you can see that if you take those partial derivatives and add them up, you're just going to get a constant of 2 in this case. Okay, so the integral that we have to do is just the integral of the constant 2. Okay, and now let's remember the region that we're integrating over. W is a solid cube. And so it's a triple integral, which means we're going to have limits for x, y, and z, but the limits are easier, okay, because of the fact that our region is rectangular. So it doesn't really matter what order we integrate in. So how about if we just go dx, dy, dz, and all of our limits are going to be 0 to 1 in this case. Okay, because our cube has sides length 1. And let's go ahead and write out the details of this integral. So we'd start with the inside. We'd integrate 2 with respect to x. That's going to give us 2x, which would get evaluated between 1 and 0. And if you do that evaluation, that's just going to turn into a 2, and we're going to be down to a double integral. Okay, and then you play the same game over again, integrate 2 with respect to y, and you'd get 2y, evaluated between 1 and 0. But that's going to become a 2, and so we're just integrating 2 with respect to z, which gives us 2z from 1 to 0. And after all that, we come down with an answer of 2. That's our flow through this cube. Okay, but then you could ask the question, did we really need to do all of that writing? Was it really necessary to write out all those steps? Well, I guess that's kind of a matter of opinion, but there is an observation that we could have made that would have made this a lot easier to do the integral. All right, we're actually going to make a couple of observations here. So first, I want you to back up to the step right here, where we were taking the triple integral w of just the function 2. 2 is a constant, so we could have just taken that 2 and pulled it outside. And what that means is if we just integrate dv, we're going to get the volume of the cube, so this integral should just be 2 times the volume of the cube. But what is the volume of the cube? If all of its side lengths are 1, the volume is just going to be 1, so we're going to get 2 times 1, which is 2. That's just a little bit of a shorter route to the answer that we got, okay, if we had noticed that. Okay, and the second observation I want to point out here, this problem that we just did is a problem that was actually done back in chapter 19. Problem 7 on page 135. I'd like you to take a minute and just do an experiment here. So maybe pause this video and take a peek back at problem 7 on page 135. Take a look at the solution, and I want you to look for 2 things when you do that. Number 1, did we get the same answer? Okay, the answer that we got is 2. Does that agree with the answer on page 135? And the second thing, I'd like you to think about which way of doing the problem was easier, the way that was done back on page 135 or the way that we did it here? Okay, try that. Okay, so hopefully you're back from having taken a peek at page 135, and what did you discover? So hopefully you confirmed that the answer of 2 that we got here, that agrees with the answer that we got on page 135. But the way that you did that problem on page 135 was very different. You calculated the flux through this cube directly, which meant you had to consider all of the 6 faces of this cube separately. There are 6 pieces to this outside surface. That was a very tedious process of finding the flux through each face one at a time. You had to add all of those together and come up with this answer of 2. Notice how much easier our way of doing this problem was. We were able to come up with an answer of 2 just using one triple integral. And so it really illustrates the power of the divergence theorem. It really makes flux integrals easy. The one catch is our surface has to be totally enclosed to use this method. It works great in that situation, but that's its limitation. Okay, and so future examples, we'll try this out and see how it works for other problems.